Hi, in this project we are going to see unsupervised diabetes analysis for 7 Indian states, and of which we are considering Uttar Pradesh and Madhya Pradesh primarily for this project. And the database readings consist of like over 751,000 records for these two states. And after cleaning the data, the number of records have dropped to 277. And then the blood sugar readings have been converted into 7 levels, or have been classified into 7 levels. From 0 to 65, it is like low sugar range. 66 to 100 is taken as 2, and the numerical value number 2 stands for normal sugar range. And then 101 to 136 as good, and so on. And the last one, 244 to 500, is like very dangerous. Before we went further into analyzing the data using k-means and principal component analysis, there are about 54 features. We want to reduce the number of features to some considerably, because not all features will be important for the readings, for the analysis. So for example, the month of birth and the age, you can consider just one of them. Year of birth can be omitted. Likewise, the weight measured, that is a true or false. So we can eliminate that and instead take the weight in kgs value. And in this way, we can eliminate many features, and use only the ones that are important and necessary. For that, in order to know the important features very quickly, a Pearson correlation matrix was projected, as you can see here. From this graph, the ones that are needed have been chosen, and we have chosen like about 11 of them, and the rest of them have been dropped. So out of this, after analyzing them, we have taken all these fields have been dropped, and the remaining have been retained for the analysis. Now, after getting the required data, we are now going to perform some normalization so that the data is standard throughout the for all the records and all columns. After standardizing them, we now apply the principal component analysis. And then in order to know the number of components, we are first going to perform some variance the explained variance graph, which tells us like about 10 components is reasonably good for us, and it will cover at least like over 90% of our data can be explained by using the 10 components of PCA. And then this is a graph for the 10 components to show us how much of data can be explained by that. So we have considered the 10 components for our data, and we have used that data, the principal component analysis information, and we have given that as an input for the k-means. So what we have done is we have given k-means with PCA data and without PCA data. Then this is the first one where PCA data was provided for the k-means, and the cluster was determined from them. The number of clusters chosen was 3 clusters. Again, that was based on the elbow method. And after taking the applying the k-means, we plotted the graph for the k-means, and here these are the clusters for just 3 components. But if we would like to see all the 10 components, this is a cluster for 3 components. If you would like to see the cluster for all the 10 components, just we have expanded it, and this is a cluster for all the 10 components. Then without PCA, directly applying the k-means on the scale data, that is normalized data, we have plotted the graph for that again, and this is the graph for that. So as you can see, this graph this also shows us the clusters, and this is with the PCA. This also shows us the clusters. What we noticed is the data that was the projection of the k-means data for the clusters was not much different from without the clusters, without the principal component analysis. So there was not much variation in our clusters, but still we can use PCA because once the dimensions are reduced, your K means the processing time is very much reduced. That was observed again when we ran this project. It took a longer and longer time, a lot longer time to generate the K means plot graph, and also to generate the cluster analysis for the K means without the PCA. So this is our data for PCA and without PCA. Then we have also projected the data for just two components, that is PCA1 and PCA2, and this is our graph, and here we can see the low, normal, good range levels for just two components and how it is distributed. Overall, we can understand that the good, that means if blood sugar level is not bad, it's all pretty good. That's the projection this is giving. And then if you projected any two like age and the weight in kgs versus age, okay, this is the weight and this is the age. If you did it this way without the PCA, you can still understand that there are some clusters here, especially the blue ones, and we also can understand that the entire scatters itself falls between 40 to weight ranges between 40 to 80, and the age ranges between somewhere between, age did not matter actually, not much, because at almost from 20 to 60 to 70 years, many of them were found to have diabetes. And it's also interesting to know that in the age group of 20 to around 30, there are quite a few people, the LOs are the ones that are at risk, so there are quite a few people even in the age between 20 to 40 who are having dangerous and above risk level uh, sugar levels. So that is something you can decipher from this graph, but mostly looking at the colors we can say mostly people showed normal to good diabetes levels, sorry, sugar levels. So these are the basic analysis that we can draw from um, projecting it, and this is a 3D projection. You can understand more things when you're projecting it in 3D level, where we are also considering the hemoglobin, age, then the height and hemoglobin. We can change the numbers here. The index numbers can be changed to see how the projections differ from value to value. So this is all about this project. If you have any questions, please contact us. Thank you.